from 5 prime to 3 prime, this small piece. Of course, at the beginning, we need RNA primer. Because RNA primer, there's no restriction. And then we have the synthesis. And how we have to do the same thing right here. Okay, this is the RNA primer. Then we using gene complementary policy, we have the synthesizers. And then we have another RNA primer synthesis. And then we have a DNA sequence comes out. So this is from 5 prime to 3 prime. 5 prime to 3 prime. Go this way, go this way. 5 prime to 3 prime. What are these called? Who find it? These called Okazaki segment. Who find it? Reggie Okazaki. 1940 to 1975. Sorry, 1930 to 1975. Only 45 years old. A Japanese, I think it's American Japanese scientist. And people say if he live another 5-10 years, he will award the Nobel Prize. Okazaki segments. That's the way they solve the problem. The bacteria, originally they all come from bacteria. Bacteria solve the problem to do the replication in the lagging band. Okay, now when these things happen, we have to connect to these, all right? So what we have to do? These RNA primer have to cut. Which enzyme we use? DNA polymerase 1. Now, by the way, the replication, we need a DNA polymerase 3. And cut the RNA primer in the lagging band for the Okazaki segment is DNA polymerase 1. Once it's cut, okay, these are all gone. We need to connect them. Okay, we have to connect them. When we connected, what we call it? Ligation. Is that right? Now, what's the enzyme? It's a DNA ligase. Very fortunately, we have a name corresponding to that. Okay, then go ahead. We have to finish. We can finish the replication. So that is basically is a story for the DNA replication. Okay, not done yet. When we finish the DNA replication, we remaining 2 questions. We have not been solved. Number 1. Topological issue. What is topological issue? When the DNA just finished the replication, you know, like this, highly twisted, is disorganized, and then we can say it is positive supercoiled. And this is not going to work. Remember, in the short life of the bacterial cell, they have to do semi-conservative replication. They have to do this immediately. And we need to make sure the newly synthesized DNA can do this immediately. Then what we should do? This disorganized positive supercoiled has to become an organized, relatively organized, negative supercoiled. And we have the enzyme for that. It's a topological issue. We have the enzyme. Topoisomerase. It is actually topoisomerase 2. There's lots of topoisomerase. And topoisomerase 2, very specific in E. coli cell. It is called DNA gyrase. So DNA gyrase, if we ask you what's the function, it is change newly synthesized DNA strand from positive supercoiled to negative supercoiled. So this is a topological issue. It solved the problem. Number 2, fidelity. fidelity issue, which means how accuracy. That's the key. We say that the good thing for semi-conservative replication is we could make sure the genetic information from mother cell to the daughter cell are exactly the same, theoretically, in the exception of mutation. However, there's a mutation happen all the time. This is the same thing like you do the exam paper. You're never going to get 100% all the time. You made some mistake. And sometimes they made a mistake too, so we have to fix it. So what's the problem for these things? Number one, the natural happen for DNA replication, the mutations, the mistakes, is actually pretty low, not very high. There's also a K-equilibrium number for that is 1 divided by 10 to the 3 is 0.003. It's not very high. However, if you convert them into the cell division, for bacterial cell division, that is about 2 errors per cell division. This is pretty high. That's not good. So, what we do, very lucky, DNA have their own function to do the fixing. DNA polymerase 3. So what happened is, you know during the replication, DNA polymerase 3 can do 5' to 3' polymerization. And we know that, we already talked. They have another secret function. They can do 3' to 5'. A 5' to 3' polymerization. At the same time, they can do opposite direction, 3' to 5'. Exonuclease. We call it exonucleation. So what this means, if you have ATGC, then you have a TACG, this is correct. If all of a sudden there is an A happens, what's going to happen? This DNA polymerase 3 could find it, and nickel this out, add a correct one. Now, of course, this rely on DNA polymerase 1 to cut it, and they require DNA ligase to do the ligation. However, at the beginning, the DNA polymerase 3, they do a screening test using their function of 3' to 5' exonuclease. They could find a mistake and fix it. And this is, we call it a proofreading. And remember, when you submit a paper, manuscript to a journal, the final step is to do a proofreading and make sure there is no grammar mistake. So this is proofreading. Is this enough? This could roll down the error around 10 to the minus 5 to 10 to the minus 6. Okay, pretty low. Pretty low level. Is this enough? No, not really. We need another one. What is the number 3? You learned in your other class, mismatch repair system. Mismatch repair system, what happened is, instead of you just find it, I'm going to label them using CH3. It's methylation, as you usually do. Methylation. You add up a marker, which is CH3, if there is a mistake. Then you cut it, DNA polymerase 1, and then ligate it, use DNA ligase. Of course, you put it back a correct one. So the last step for the mismatch repair system, they could load down to the error, is about 10 to the minus 7 to 10 to the minus 8, and close to 10 to the minus 9. Error per cell division. This is very low. This is very low. And this is important even for the human being. For example, the colon cancer, the most likely is caused because of the mismatch repair or the mismatch during the DNA replication. If your body cannot fix it, you end up with colon cancer. And at the time, people find the sample, their rate is pretty high. It's 10 to the minus 5 to 10 to the minus 6. So if you do not have the last mismatch repair system, you end up with here, as a human being, you could end up with colon cancer. Okay? So this is something very important. Now we haven't shared with you a story. So also Cronenberg find the DNA polymerase by the time he claimed he found the DNA polymerase. And it's very interesting. Then people have to do research to verify it. Is that right? It's DNA polymerase. So what do? They use a mutation. Okay, if a bacteria, let's say, I have this sequencing. This is DNA polymerase. I'm going to find some of the bacteria is mutated. Which means a mutation. They don't have this DNA polymerase. And I'm going to do the research for DNA replication. Is that still working? They want to see whether it is still working. And surprisingly, they find it all works very well. So what this means? Which means also Cronenberg, this DNA polymerase is not really a major DNA polymerase. And this has happened when he awarded the Nobel Prize in 1969. Then people start to do the verification study to find whether this is really a DNA polymerase. And which means it's a major DNA polymerase. And they do the mutation, they do the same replication, they find it's still working, which means what he finds is not really DNA polymerase. Then what is the thing he finds? So what he finds ends up with a primase. Of course, it has a polymerization function, but it's much minor function. So that's a little bit joke in the history. However, he had a big contribution, I'll tell you. His son is Thomas Cronenberg, discovered DNA polymerase 2 and 4. And his youngest son, Roger Cronenberg, do the complete research of RNA polymerase. And this is 2006 Nobel Prize. This is a big, good family. So there's a little bit of story behind this. Okay? So, end up here, we almost finished talk about the DNA replication. That's a whole story from the structure, from the mechanism of all these things. We can go back to see the slides real quick about all these things. And we mentioned the DNA structure. This is right here. There's going to be the base pair, which is adenine with thymine, guanine with cytosine connected with hydrogen bonds. And this is how they connected. And by the way, the bonds connected, we call it the diester bonds, phosphate diester bonds. I forgot about that. Now make sure you understand the DNA runs in opposite direction, which basically means the sugar direction, 5-carbon sugar direction, the indication. And this is another figure which gives you to see it's an anti-parallel, semi-conservative replication. It's so clearly right here. Everything for bacteria, it's circular. For eukaryotes, it's possibly linear and coming from a replication fork and end up with a termination signal, which is TER. And this is, they see the micrograph of the E. coli chromosome during replication. This is a big deal, and I already spent time to talk the whole story there, which is the function of the enzyme during the DNA replication, including DNA polymerase 1,3, ligase, primase, gyrase, which is also we call the topoisomerase. And the whole story, Okazaki segments, all the story behind that. And you can read through all of these. It's basically a structure, it's a process, repeated what I do, what I just said. I just don't read through it, I don't like it. And then, this is a really good figure, a very good table. The table tells you all these functions described really well. And topoisomerase 4 and the gyrase, then A, then B, then C, primerase, it describes it very well. Here's a picture well tells you why we have to do from 5' to 3'. It's right there. Look at here, this is free available hydroxy bonds. And they hydrolyze 2 ATPs. They can connect it. Can they do the opposite direction? You can't do it because there's no free available OH in the other direction. And by the way, from the energy standpoint, is not working. Because they work this way, they do not work on the other way. If on the other way they have to work, they have to break down some other bands. It is hard. I give you the example, like you go to see a movie. Is there people all in the line gonna say, okay, come in, I'm gonna pay you? No, it's not gonna happen. Generally speaking, so same for the bacteria. And this is basically the DNA polymerase, the structure. It is also a hollow enzyme. We have another hollow enzyme, which is RNA polymerase. We'll talk about detail on Thursday. This is each of them, helicase, single-strand binding protein to polyisomerase, what's the function? And this is the picture is really good. The figure is really good on the top. Tells you the story, what it is happened. And this is better than lots of the publisher, I will say. They start from 3' to 5'. This is leading band, it's lagging band, and they go opposite direction, and this is RNA primer, which is Okazaki segment. This is a really nice picture. And then this is continue to talk about DNA synthesis, and this talks about the ligation of the Okazaki segments, and the DNA polymerase 1, you cut the RNA primer, and then you fuse a niche with ligation, which is DNA ligase. And this is a proofreading. And that we said you have a mistake. There's an error. You have to do the proofreading, which is by the DNA polymerase 3, and this is what happened. But they say this is not 100% efficiency because we need to follow up by the mismatch repair system. Now, by the way, if this mismatch repair system is also failed, which means a life-threatening situation, then what we have to do? Initiate the body, have to initiate DNA polymerase 4 and 5. That's called SOS recovering mutation recovery system. You should learn in your other classes. This is which means the whole body as a human being is going to working to fix it. Okay, there's other mechanisms like a bypass or those things. I used to teach, I said, it's very simple. You're from Pittsburgh to Morgantown. Highway 79, if there is a construction, what do you have to do? You may go 19, is that right? It's called a bypass. And the same for the bacteria. They have a bypass fixing, alternative pathway to them. That is also the reason why DNA mutation, and we are using anything to attacking bacterial DNA is usually the least function to curing bacteria because they have lots of the recovery system can combat it. It is also showed up here. Termination, which is when you see the TER and then they separate. It's pretty straightforward. So we end up with here Thursday, we're going to talk about RNA transcription and translation. Okay?